It's time to take a look at the 2024 AP Chemistry exam questions. The free response questions have just been released, and now we're going to walk through the answers. Hi there, my name is Jeremy Krug, and this is my walkthrough for FRQ question number 3. I need to let you know that I don't work for College Board, and this is not an official answer key. You'll need to wait a few months for that. I'm just a guy who's been teaching AP Chemistry for the past 24 years. And if you're getting ready for next year's exam, then check out my full AP Chemistry course videos right here on YouTube, as well as my comprehensive review materials along with exclusive tips and tricks over at ultimatereviewpacket.com. Now, let's get started.
FRQ question 3 is another long one. This is worth 10 points in the big scheme of your AP score. Sterling silver is an alloy that is commonly used to make jewelry and consists of 92.5% silver and 7.5% other metals such as copper by mass. Over time, the alloy can form a tarnish of silver sulfide when it reacts with hydrogen sulfide, as represented by this equation right here. Part A says, what are the oxidation numbers of silver in silver solid and silver sulfide solid? Well, if you learned about the redox reactions, hopefully you remember that any element in its natural state, or any element by itself, is going to have an oxidation number of 0. So the silver is going to be 0 when it's silver metal. Now the silver sulfide, it's in a compound, so we have to look at these charges here. Sulfide is a -2, so that means that the silver has to be a +1 in that compound. Now moving on to part B, it says the following table contains the atomic radii for silver and copper, and we have those here. And it says explain why sterling silver is better classified as a substitutional alloy than as an interstitial alloy. And so if we think about the types of alloys, this is a substitutional alloy because if you look at the atomic radii, they're honestly rather similar to each other. They're not that different. Because of that, these copper atoms are going to be way too big to fit inside those little tiny interstitial spaces between the individual silver atoms. And so instead of the copper trying to squeeze between those silver atoms, what's probably going to happen here is that those copper atoms are going to substitute in place of some of the silver atoms in that alloy. So that's why this is a substitutional alloy. If you don't know about substitutional or interstitial alloys, I have a video about that in my complete course of AP Chemistry right here on YouTube. Now part 2 says using principles of atomic structure and Coulomb's law, explain why silver has a larger atomic radius than copper does. And so the idea here is we have to consult the periodic table, and we see that silver is farther down on the periodic table. So this tells us that silver has 5 occupied energy levels, or 5 electron shells, whereas copper, being in period 4, only has 4. And so because of that, the distance from the nucleus of silver to its valence electrons is going to be larger or greater than that of copper. And so we can add that the Coulombic attractions between the silver nucleus and its valence electrons are going to be significantly weaker than those attractions would be for the copper atom. So that's going to allow the silver electrons, especially the valence electrons, to veer a little bit further out. And so silver is going to have a higher atomic radius there. Now, the next question talks about tarnish. The silver sulfide tarnish on sterling silver can be removed until only sterling silver remains. A student weighs a tarnished sterling silver sample both before and after removing the silver sulfide and records the data in the following table. So we have the mass before the tarnish removal and then the mass after the tarnish removal. And the question says, assuming that only silver sulfide solid is removed, calculate the number of moles of silver atoms removed. So for this one, we're going to have to find out how much we removed. So the way I do that is just to subtract. I take the 409.21 grams that we started with and subtract the 398.94 grams that we ended with, and I find that I removed 10.27 grams of silver sulfide. So now I can take that quantity and convert it to moles of silver. So way down here at the end, I'm going to have moles of silver. And so my first step in any stoichiometric process is to convert to moles if it's not already in moles, right? So in my first conversion factor, I have to put grams on the bottom, and 1 mole on top. And it actually tells me up here that the molar mass is 247.80. So I'm going to plug that in here. I can cancel grams top and bottom, and I'm in moles of silver sulfide. And now I can convert to moles of silver using a mole ratio. So silver sulfide needs to go on the bottom, and then silver goes on top. And I can just look at the formula for silver sulfide and see that every one formula unit of that stuff is going to have 2 atoms of silver. So 1 silver sulfide for every 2 silver atoms. So we have a 2-to-1 ratio. I can cancel silver sulfide top and bottom, and now I'm in moles of silver. So all I have to do is multiply and divide, and I find that the answer is about 0.08289 moles of silver. So that's the answer to part C right there. All right, let's move on to the next part here, and we're going to move on and talk about rhodium. So here's an element we don't discuss every day. Rhodium plating is a process used to protect sterling silver from tarnishing. This includes electroplating, or depositing solid rhodium onto the surface of a metal from an acidified solution of rhodium-3 sulfate solution. Oxygen gas is produced during the process. Now we have some half reactions here that help us to figure out what's going on. And part 1 says to write the balanced net ionic equation for plating rhodium solid from the acidified rhodium sulfate solution. So the first thing that we want to do is realize that oxygen gas is being produced. It says that up here in the header. So that tells me that this second half reaction has to be flipped so that the O2 gas is a product. And so I'm going to flip it so that 2 waters yield oxygen plus 4H plus and 4 electrons. And the first half reaction is going to stay the same because we're trying to create rhodium metal, as the problem says. So that reaction is going to stay as it is, or that half reaction stays as it is. Now, if we look at these, we can see that the first one is losing electrons. So this is an oxidation, or it's the anode in this electrochemical process. In the second half reaction, we're gaining electrons. So that sounds like a reduction, or the cathode in an electrochemical process. Well, now we're ready to add these together. There's a little problem here. We have the electrons that don't really cancel out. We have 4 versus 3. So we're going to have to multiply these equations in such a way that they add up to, or that they have the same number of electrons. So I think we need to get 12 electrons on both sides. I'm going to multiply half reaction number 1 by 3, like this. And I'm going to multiply half reaction number 2 by 4, like this. And so now we have 12 electrons that can cancel out, and I can add these together. And when I clean it up, it looks like this. We have 4 rhodium-3 plus ions aqueous plus 6 water molecules liquid yields 4 rhodium atoms solid plus 3 oxygen molecules gaseous, plus 12 hydrogen ions aqueous. And just so you know, if you leave off the states, those state symbols, that's okay too. That's just icing on the cake. Now, part 2 says, calculate the value of E cell for this reaction. Well, we know that E cell is the E of the cathode, or the reduction of the cathode, the potential minus the reduction potential for the anode. And the E of the cathode is given to us, that's the rhodium, so that's the 0.80 that I put in here. And then the anode value is the water and oxygen half reaction, which is 1.23. So that goes in the second position. And so when I subtract this, I find that 0.80 minus 1.23 gives me a total E cell of about negative 0.43 volts. Now, some students will see that and get a little bit flustered or concerned because we're used to having positive E cells. And that's true, but that's because E cell is positive in a galvanic cell. This is not a galvanic cell. This is an electrolytic cell because we are electroplating something here. So this is different. Now, the next part actually kind of helps us go into that. In fact, it says, based on your answer to part D3, explain why this process requires the use of an external power source. Well, if we look at the E cell, it is a negative value, isn't it? So that tells us that this process is not thermodynamically favored. And if we're not sure about that, the equation delta G equals negative NFE will confirm that. Whatever the sign of E cell is, the sign of delta G is the opposite of that. So if E cell is positive delta G is negative. Well, in this case, E cell is negative, so delta G has to be positive, which means it's not thermodynamically favored. And because of that, that external power source, a battery or some other electrical power source, is required to power this. Part E says, calculate the length of time in seconds required to plate 2.8 grams of rhodium solid onto a piece of sterling silver if 2 coulombs per second of current is applied. So we have to remember that the equation I equals Q over T will help us here. I is the current, which is 2 coulombs per second, or 2 amps, as we usually write that. The time is what we're asked to solve for. We are given the 2.8 grams, but what we'll have to do here is convert the 2.8 grams of rhodium into coulombs using stoichiometry. Now, the first step of that is to convert to moles. So grams on the bottom, 1 mole on top. There are 102.91 grams in a mole of rhodium. I looked that up because I don't use rhodium all the time. Grams are out. Then we have a mole ratio. And if we go back to that half reaction involving the production of rhodium from rhodium-3 ions, we see that rhodium's on the bottom. It takes 3 electrons. There's a 3 in front of that electron in that half reaction. So that's why it's a 3-to-1 ratio. The rhodium is out, and now we're in moles of electrons. The last step is to convert to our final unit, which is coulombs this time. So coulombs has to go on top, moles of electrons on the bottom. And the number of coulombs in a mole of electrons is Faraday's constant, 96,485 coulombs in 1 mole of electrons. That number is or was given to you on the equation packet. So moles and electrons cancel out, and when you multiply and divide, we find that we're going to have about 7,876 coulombs. I'm going to round at the end here in this case. Now I can plug into the equation current equals coulombs of charge divided by time in seconds. The current is 2 amps. I know it says 2 coulombs per second. That's the same thing as an amp. That's how we usually write it. The charge is 7,876 coulombs. And the time is what we're solving for. So using simple algebra, we find that the time is about 3,900 seconds. We don't have to convert this to minutes or hours or anything like that because it says convert it in or calculate it in seconds. So 3,900 seconds is the answer. And so I hope you did well on this question. There was a lot going on here, a lot of good electrochemistry, redox. We had some Coulomb's law, a lot of stoichiometry in here. If you liked my video and learned something from it, please smash that like button, and hope to see you back very soon when we're going to go over question number 4.